Let's take a look at what is going to result from revolving the area bound between y equals x squared plus 1 and the line y equals negative x plus 3. And we're going to try to compute the volume of the resulting solid. Well, we do know that the equation y equals negative x plus 3 is just going to be a downward sloping line with a negative 3 or with a positive 3 intercept. And then we also have the equation of a parabola there, x squared plus 1, which is just a parabola that's centered about the y-axis with a plus 1 y-intercept. I always like to try to sketch these out by just mirroring the picture first. And then from here I have a little bit of a reference from which to draw in those discs or washers. So you can see I'm just going to grab a point, I'm just going to kind of rotate it down to its equivalent point underneath the x-axis. And then this gives me a little bit of a basis to begin kind of sketching out what this might look like. And it's going to be really helpful because we know that each of those little tiny widths there are going to be the d something part of our integral, dx in this case. And I'm going to sketch this one more time just so you can kind of get an idea of what it's really going to look like if I didn't have those axes or the other parts of the function in the way. So now here's a graphic that is a lot more of a computer-generated, clear to see idea, but you can see kind of that we have that right sketch in mind, that we're just taking those small little widths and that we're just rotating those around to get, in this case, what looks like little washers on the inside of our region. Now, one thing to keep in mind is although these are washers, we've already said that that washer method is really just the disk method. It's taking one solid shape and subtracting another solid shape from it. So here you can see that we kind of have this truncated cone that is our larger shape, and we're taking away something that looks like, oh, I don't even know, a spindle, maybe some kind of spindle shape. And so we're just going to write this as finding the volume of the first solid using our disk method, those tiny little cylinders that are of the structure pi r squared h, but we know to replace r with f of x now, and dx is going to be our height. And we're going to do the same thing with that other solid. So we're going to do the exact same thing. We're just going to subtract the two volumes. But there is one thing to be careful for. Although you just want to kind of write it in here, as I did, that f of x, we really want to make sure that we're differentiating, that we have an f of x and we have a g of x. They're two different functions. One is going to be on the inside after this rotation, and I'm just going to call that g of x so that I keep it consistent in my mind. So here we have, again, that f of x is going to be that outside function. We'll call that f of x. And then we're going to call the other one g of x. Well, now we can just simply plug in what I know. So f of x is going to be that outside function, which here looks like it's going to be the line. This is where a picture is really going to be helpful. And so we're going to write that in as the bracketed negative x plus 3. Again, those brackets are very helpful. Don't forget to include and continue your notation so that you don't accidentally forget that squared part. And we're going to do the exact same thing with g of x. That's just going to be our parabola, but now it's our parabola equation. Oh, wait for it. Squared. I think I do that in the next line. Give me a second, I'll catch it. Again, because this is an integral is just addition. It's infinite addition. It's adding infinitely many terms that are all infinitesimal in size, but it's still addition. And so we can factor out that pi, because if I'm adding many things that are all being multiplied by pi, it's the same thing as me adding the many things and then multiplying by pi, right? We have that distributive law of multiplication and addition, so I can always factor out that pi. So here we're just taking a look at how we can solve this out. We're going to have to solve this by FOILing, right? Or what I like to call double distribution. This multiplying and then multiplying again but we're going to be trying to expand this out and get it into something that we can find an antiderivative for. And right now, as a polynomial, it's going to be very easy to do that derivative, that antiderivative. For the x squared, it's just going to be 1/3 x cubed, right? This reverse power rule. And in fact, that reverse power rule is going to be applicable for every single term as we work through this. Notice that we don't know where the bounds are yet. A and b aren't something that is always going to be 0 or is always going to be a positive number. We really have to be careful about those, and we haven't really dug into that part of the problem yet. So we're just carrying it through as a and b for right now. Now, one thing that we can do that I'm going to start to do here is I'm going to try to just plug in the b value, and then I can subtract all the a values. But we know that there's a number. There's a number that actually goes with b and goes with a. So instead of writing what would probably be at least a 2-line long equation, why don't we take some time and go back and find out what b and a are first? And that way, whenever we're plugging it in, we can use our calculator to keep it as a number. And that'll save us a lot of time when we're doing our computations. Now, as a side note, since this region is being bound by two functions, that means it's going to stop the moment that those two functions intersect. Well, we can find out exactly where those intersections happen by just finding out where the two lines are equal to each other, the two curves, excuse me. They should be called curves. So we're going to set the parabola equal to the line, and we're going to try to solve out for where those x values are. Those will be our a value and our b value that we want to put into our integral. And so now we found out that that's going to be a value of 1 and -2. And I've done this just by some simple factoring. You could use the AC method, you could use the quadratic formula sometimes if it's a little bit more difficult than this one, but I could just recognize this one off the top of my head. A little bit of a note, make sure that whenever you are factoring something that you don't just stop at that x plus 2 and x minus 1 level. You really want to say that x plus 2 is equal to 0. That could cause the whole equation to hold, and so that's going to happen when x is -2. Be careful of that little sign change. Well, now I'm going to choose to just squish everything together, and I can do that again because integrals just mean addition. But actually in this case we've already done the integral, so really we're just factoring a pi out of both terms and then distributing that negative sign through. But that is a little risky because sometimes you forget to do that negative sign. So here's what I would rather you do. I'd rather you keep the two brackets separate. So evaluate one of the brackets and do that as an entire integral, get a number, and then in the other bracket get another number. That way you only have to worry about that negative sign once, and it's a little bit less prone to error. So now we just get to plug in our bounds. Keep in mind that we're, again, trying to keep parentheses and brackets where they're appropriate. They are our friends, and they're going to help us from making any mistakes with those negative signs. So here I've chosen to just do the upper bound in a parenthesis, and then I'll subtract when I'm evaluating it at the lower bound organized. Now after all is done, you can plug it in your calculator and you get that it's going to be equal to pi times 23.4. And again, just to kind of put that into context, that's the volume, the size in cubic units of this shape we created by rotating around and creating many, many, many miniature, infinitesimally small cylinders.